Okay, yesterday we have seen some basic potential estimates that work for general quasi-linear equations and quasi-diagonal structure systems. And these estimates read as follows. This is the Riesz potential, and then you can pointwise bound the gradient via the Riesz potential and in the following way. And therefore this estimate essentially brings the whole theory back to the linear case. And also continuity criterion given, and the new fact, the most recent fact is that this also holds for systems. And this was a very long-standing fact which was open in the theory, because also for you, estimates were not known for systems. Okay, now I'm briefly showing you what is possible to do in the parabolic case. The parabolic case is much more technical and requires, not surprisingly, the use of so-called intrinsic geometries developed in the 80s by Emanuele di Benedetto. Okay, the model case is once again the P-Laplacian equation, the evolutionary P-Laplacian equation, and you see that now when P is different than 2, already in the case of a zero right-hand side, this equation is not homogeneous, because this, the evolutionary parts case with power 1, this case with power P minus 1, and therefore you cannot expect homogeneous estimates. In particular, you can't expect estimates of this type, which are, for instance, homogeneous when mu is 0. This is a homogeneous estimate. This you cannot expect even when mu is equal to 0, because you cannot get homogeneous estimates for non-homogeneous equations. Otherwise, you scale and you immediately reach the fact that every solution is 0. This is a standard fact. Okay, the notion of solution I'm going to treat is, as usual, the one of Sola. And the basic result is by Boccato, Dall'Aglio, Gallurri, and Ursina, which claims that a solution, there exists a solution. This result will be now recovered by means of potential estimates very soon. Okay, first of all, we have to redefine the Riesz potentials. The standard caloric Riesz potential is now given in the following way, where these are the standard parabolic cylinders. Standard parabolic cylinders are exactly these ones. They scale, the time direction is stretched as a square to compensate the lack of one derivative. So when you scale from QR to Q1, then the equation scales accordingly. That's the idea. It's not difficult then to prove that this estimate holds for the heat equation. There's a number of ways you can prove it, for instance, by direct comparison, by Duhamel's principle. Anyway, this is the estimate you get. So essentially, for the heat equation, you can go straight on along the usual path, along the usual elliptic path. Okay, what happens when P is different than 2 now? When P is different than 2, now you have a real problem, because, for instance, you cannot get homogeneous estimates. And this is a sample of what happens when you do consider standard parabolic cylinders. When you do consider standard parabolic cylinders, you get estimates that are not homogeneous, and the non-homogeneity is exactly the rate of the scaling deficit of the equation. Here you see power 1, here you see a gradient to the power P minus 1. So it's homogeneous if and only if P is equal to 2, as you would expect, of course. If you can imagine a potential estimate for an equation like this, and this is for an equation like this, and this is now our next aim, of course, when mu is equal to 0, after all, you have to recover this estimate. So first test is that this estimate should be recovered. Okay, these are the intrinsic parabolic cylinders that I already described in the second lecture, I guess, or in the first lecture, I guess. Okay, standard parabolic cylinders are given when lambda is equal to 1. Otherwise, you introduce these intrinsic cylinders that are further stretched in time by a factor of lambda. Okay, let me just say that I will just consider now, for the sake of simplicity, P larger than 2. you see when lambda is very large, these cylinders get thinner and thinner, because when lambda is very large, the idea is that a cylinder is intrinsic if and only if a relation like this holds in a certain average way on the same portion of space-time. So that's where the terminology intrinsic stems from. And essentially, this tells you that if you are on a portion of space-time where du is like lambda, then you can make confusion between du and lambda, and then you get this heat equation with a different diffusion coefficient. And here you see what happens when lambda is very large. You get a lot of diffusion. That's why you need less time to diffuse the heat with respect to the heat equation. That's the idea. The basic idea is that if lambda is very large, these cylinders get thinner and thinner in time because you have a lot of diffusion, so you don't need a lot of time to spread the heat with respect to the heat equation. Okay, so the whole analysis then goes through these intrinsic cylinders. From a conceptual point of view, this goes in the wrong direction with respect to potential estimates. Because the idea of potential estimates is to forget that you are dealing with the solution, that you are dealing with an equation, and you just get the estimate, so you decouple the equation from the data. But of course, if you're bound to analyze the solution on portion of space that depend on the solution themselves, this is really counterintuitive with respect to this fact. Because on one hand, the philosophy of this estimate is that you want to just have a representation formula as you have convolution, so therefore you want to decouple the solution from the data, while this forces you to look at the solution once again. So we have to find, first of all, a suitable formulation of potential estimates that is going to catch this peculiar fact. Okay, and why these cylinders are important? Because we have seen that if you use standard parabolic cylinders, then the estimates are not homogeneous, and they cannot be. But if you use intrinsic cylinders, then estimates become homogeneous. Homogeneous means that you are, for instance, here you are estimating du in average with lambda, and then a controlling average improves in a pointwise control, that is a controlling L infinity. That's the usual L infinity LP minus 1 inequality. For instance, in the elliptic case, this is a standard consequence of the usual elliptic estimate. The usual elliptic estimate is, if you forget about this, then if you assume that this guy is less than lambda, then this guy is less than lambda. So this is the way that the thing is. Of course, this is a conditional assumption because lambda appears both here and here, but this is really a finer estimate than this one. In fact, once you know this estimate, then the previous estimate follows on every cylinder. So this is the right estimate to look at because it reproduces, in a sense, the local geometry of the equation and of the solution. Okay, this is the inspiring fact for potential estimates. So therefore, we proceed in defining so-called intrinsic Riesz potentials. Intrinsic Riesz potentials are nothing but the usual caloric Riesz potentials, but using a certain stretched cylinders. So at this stage, lambda is just a parameter. You are free to choose as lambda as you like. There's no reason to call them intrinsic because you're not linking to the solution itself. So just take it as it is. It's just another way of stretching the Riesz potential. This is nothing but this. Okay. Note that when lambda is equal to 2, or when lambda is equal to 1, or p is equal to 2, then this recovers the usual caloric Riesz potential. That's the basic idea. Okay, and then this is the estimate that we get. The estimate is exactly the previous estimate of Benedetto and Friedman, but takes into account the Riesz potential. Now the point is the following. Take lambda. If there exists a lambda such that this guy plus this guy, and they both depend on lambda on the left-hand side too, is less than or equal than lambda, then you get a bound on this quantity. Observe that in the elliptic case, this is exactly what you get from the potential estimate. Imagine that the sum of the right-hand side is less than or equal than lambda, and then This guy is less than lambda. So that's essentially the best way to get a potential estimate. Of course, it's once again a conditional estimate, because it tells you that this estimate holds provided you are able to verify this condition that involves lambda both on the left and the right hand side. But this is really the best you can get. Okay, so is this estimate sharp? The answer is yes, if we show that it reproduces the behavior of the fundamental solution. So potential estimates are, a replacement of convolution inequalities when fundamental solutions cannot be used to get new solutions via convolutions. So the very basic thing you should do to check the optimality of this estimate is that if it reproduces the behavior of the fundamental solution, let's say of the solution when the right hand side is a Dirac charging 1 point, then this estimate will be sharp. That's the idea. Of course, a first hint of the fact that the estimate is sharp is that if the solution is time independent, you reduce to an elliptic equation, and then this reduces to this. This should be already, sufficient to say that this is the right estimate. But let's say if it reproduces the fundamental solution, and the fundamental solution is this function, that's the Barenblatt solution. That's one of the many Barenblatt solutions. Every evolution has its Barenblatt solution. You see that this expresses the finite speed propagation with the evolutionary P Laplace equation. And okay, this follows by classical work on Barenblatt by direct computation. Don't try really to read all the exponents. You should just trust that this is the solution. But otherwise, it's a lengthy computation. But it's a computation. It is what it is. Okay, the Barenblatt solution exhibits this behavior, this asymptotic behavior, at zero, at infinity. So it decays at infinity in this way, and it blows up in this way. Now, the point is that forget about the Barenblatt solution, and the estimate that we prove says that this behavior is satisfied for any solution with respect to any general equation now of this type, so without direct computation. So you take a divergence of A, X, T of the U, and then this is satisfied with Dirac here, and this is satisfied by any solution, and this is a one-page proof corollary of the previous estimate. So this tells that the estimate is the best you can get. And now, this is a conditional condition because you see lambda appears both on the left and on the right hand side, but nevertheless, now you see that if you start from this, another half a page proof then leads to the following, let's say, non-intrinsic estimate that works on any general parabolic cylinder. In particular, when mu is equal to 0, this perfectly recovers the Benedetto-Friedman classical estimate. No surprise. That's the proof. Okay, the proof of these estimates is rather complicated. Essentially, you have to exploit every single fact from the theory of evolutionary P Laplace equation. It takes something like 80 pages all in all. But once you have this, then you can recover any qualitative property of the solution whatsoever you can imagine. All kinds of regularity are now follow from these kinds of estimates, because essentially they once again play the same role that the previous estimates they were playing in the elliptic case. That is, they reduce the theory to the linear case, to a linear theory. In particular, for instance, we have that if this object goes to 0, if the Riesz potential goes to 0, now this is not an intrinsic Riesz potential. This is observed that also here, this is not the intrinsic Riesz potential. This is the real caloric Riesz potential. Because that's the point. And this is exactly the same estimate you have for the heat equation. And then you have these two corollaries. If the standard caloric Riesz potential, because you finally get rid of this intrinsic factor, if it goes to 0 uniformly, then du is continuous. in particular, if you have such a concentration of the measure, then U is locally Elder continuous. In particular, we also have a nonlinear parabolic Stein theorem. That's what we said yesterday, the classical theorem of Stein. This is a very classical fact for the Laplacian. I will talk about it now later. What we call it, this is a classical theorem of Stein that tells you that if this belongs to Ln1, then the U is continuous. This is the classical theorem of Stein. So this is the smallest rearrangement invariant function space amongst these Lorentz, for which you can get, say, the dimensional analog of Sobolev embedding up to the continuity. That's the borderline case. So in the first step with Tuomo, we proved that this still holds when you get the P Laplacian. So there's no difference between the P case and the heat equation. And now it also follows from the from the previous estimate as a very short corollary. We get the full thing. And this is observe that this is just the parabolic dimension. That's the parabolic dimension is n plus 2. So in this case, if belongs to Ln plus 2, then this is continuous. Of course, this doesn't catch the elliptic case because there's a difference between Ln, and Ln plus 2. But also our argument tells that if this is equal to F, and F is, for instance, independent of T, then this improves to this, and then you go to the elliptic case. Essentially, this happens because when it's T-independent, then you can approach the asymptotic profile. Otherwise, no reason to approach an asymptotic profile if you're already changing in time. You have a forcing term with time, you never approach an asymptotic profile. But if you have the asymptotic profile, and this happens, for instance, when the right-hand side is T-independent, then you get the elliptic case. Okay, and now finally, we go to the most recent results, and we finally connect the classical partial regularity theory with the potential theory. So this was a short presentation of the parabolic aspects of this new linear potential theoretic developments. And now let me recall this recent paper we had again with Tuomo. If you have the P Laplacian system, then you get the potential estimate. So now the idea is that is there an analog approach for general systems? The answer you have seen yesterday is obviously not, because even when the right-hand side is the best possible, that is 0, then solutions get singularities. But still we can do something. And so now we want to connect the classical partial regularity theory stemming from the original works of De Giorgi, Morey, and Giusti Miranda with the potential theory. So the idea is that we want to find a formulation to describe partial regularity properties in an optimal way, but using potentials. And this is what we get. In particular, we want to recover all the corollaries. And this is what I was saying. Solutions to homogeneous systems are in general singular, and this is a very old fact known since De Giorgi, Maziane, Riesz, and counterexamples. Most recent ones are by Zverak and Jan. They prove that solutions can be unbounded. There's also a recent paper by Mooney and Connor Mooney and Video Saving, where they decrease the dimension, proving that the gradient can be discontinuous under minimal dimensions. Okay, so I will consider now these assumptions, which are the usual assumptions, but this which is slightly stronger, that's the continuity with respect to the first derivatives. And this essentially, it's natural because it serves to linearize. But these are essentially the assumptions that we considered before for the p equals to 2 case. So the classical partial regularity stamps that although you have singularities, these singularities cannot go beyond a negligible closed set called the singular set. So there exists a full measure open subset omega u that depends on the solution, of course, such that the solution itself is Hilbert continuous with, under these assumptions, any exponent beta less than 1 in omega u. This is called the singular set, and okay, what it remains is called the singular set, and omega u is called the regular set. It's essentially the union of all the points such that there exists a small neighborhood or a small ball such that the gradient is regular in the small ball. The pioneers were the Giorgi, essentially the idea of proving that you have a small, subset of singularities. It goes back to the work of the Giorgi on minimal surfaces. Then Justin Miranda and Maury then adopted the same philosophy and more or less the same approach in the case of systems. Okay, how do you prove this? The idea is to use the access functional that we already encountered in the second lecture. Is the usual way of measuring the oscillations of du in a small ball. It's nothing but the mean square deviation of a function from its average. And then the regular set is actually given by the following very suggested condition. So there exists a universal, under these assumptions, a universal epsilon that depends just on the ellipticity constant and on the rate of continuity of the derivatives of A. So it's independent of the solution, such that if there's a scale where the oscillations are small, then they will be smaller and smaller. So you just make this test on one scale, and then the other scale, the other scale follows. So that's the basic idea. So this essentially tells you the general philosophy of vectorial elliptic theory. If you want to produce a singularity, you have to have a certain universal amount of energy. Below this certain universal threshold of energy, then singularities are smoothed out by diffusion. That's the idea. So this is a general principle. I mean, you need a certain amount of, a certain minimal amount of energy to produce singularities. Otherwise, singularities are not there. So in the scalar case, are never there because you can essentially show that this is always small. That's the basic idea. And in particular, this implies the partial regularity I was talking about, because by standard Lebesgue theory, you know that this is small as you like, almost everywhere. So this plus standard Lebesgue theory tells you that this happens almost everywhere, and therefore you have almost everywhere regularity. This set is open by definition, observe, because if this is small at one point, then you tilt a bit around the point, and by the absolute continuity of the integral, then you can still show that this is strictly smaller than epsilon. So the openness followed by the definition. So it's the same method that proves simultaneously that the set is open, and the fact that the set is full measure follows by standard Lebesgue theory. So these are the typical 2 points that you have. As a matter of fact, you have that this is essentially where this guy is actually 0. If you just catch one small scale where this is small, then it's small forever. This is just a rewriting of this. Okay, what happens in the possibly degenerate case, we reproduce the same assumptions as before, nothing different, but now we take into account vector fields which are modeled on the P-Laplacian vector field. And in addition, we have to prescribe a degeneracy that actually I first encountered in a paper by Giuseppe Mingione many years ago. This tells you that we have a degenerate system, but it degenerates at the origin like the P-Laplacian operator. Otherwise, you are prescribing essentially nothing, because you could degenerate at every point, so there's no reason to have any regularity at this stage. Then The new excess functional can be now reshaped according to the growth, and it becomes the following one. And this is once again something that I first met in a paper by Fusco and Hutchinson in '85, I guess. But anyway, this is, you see, it's a double phase excess functional because it scales like P, but it linearizes as the square because P is larger or equal than 2. So it linearizes as a square. Anyway, this is just another way to measure. It's just the proper excess functional you want to consider for this problem. Okay, then there's this theorem of by Duzar and myself where we proved that this can be proved also for minimizers of quasi-convex functionals and for general systems by p-harmonic approximation. So this tells you that under these assumptions there is partial regularity. So nothing different from the standard case. Exactly as before, you see that this functional, when p is equal to 2, it's exactly the usual square excess functional. Otherwise, it is what it is, but it works. And using this functional, you can reproduce the whole theory in a nice manner, getting that you are, continuous outside this open set, which you can prove that is full measure. Once again, we also in this case, you can provide that there is a universal epsilon. Okay, now, okay, what is the philosophy? What is the philosophy of partial regularity? The philosophy of partial regularity is that you are actually linearizing a system. That's the basic idea of going back to the geology. So the basic very simple idea is essentially that there's only one system you can really treat. That's the Laplacian system. That's the only system you can treat. Then the Laplacian system you can write down as the divergence of the gradient. And you can believe that if you put a constant matrix, nothing happens here, provided the constant is elliptic, the matrix is elliptic. It's just a change of variable. So essentially, the only systems you can really very well treat are the linear systems. Now, what do you do if you have a general nonlinear system? If you have a general nonlinear system, you take a small ball, the R centered at x0, and you linearize around this. So linearizing means that instead of treating this object here, you take this guy, you take the first order Taylor expansion, actually the second order Taylor expansion, but the first order for A. And so you replace this guy by what? By the best you can do. You take the derivative of A here, and then here you put the average of the ball here. That's the best you can get. Now this system is elliptic because A is elliptic and its differential is elliptic. This system can be treated because it's of this type. Now if this system is, okay, you know that the basic fact in elliptic theory is that they are stable under perturbations. So stable means that if two operators are closed, then solutions are closed. That's the basic fact that follows, even via Fourier transform, blah, blah. So then now you see that if this object is close to this guy, then elliptic theory tells you that the original solution should be close to this solution. But if this is good, then the original solution should be good. How do you prescribe that these two objects are closed? Well, A, it's obviously close to its linearization, provided its argument is close to the point where you are linearizing about. This is just Taylor. You can very well approximate a function with the Taylor expansion, provided you are close to the point you are developing the Taylor expansion to. So what does it mean that you are close to the point? It means that du should be close to its average, right? But being close to the average, you want to express this in an energy way. And the idea is that expressing this means that you take du, you subtract the mean square deviation, and you prescribe that this is small. Of course, implementing these takes technicalities, because you see, being close here means in L infinity, but being close here means in L2. But it's standard, again, once again, for elliptic theory, that L2 estimates, they commute in uniform estimates L infinity. So the basic idea of partial regularity is something which is close in L2, it's close in L infinity, but if it's close in L infinity, then you can really linearize, and then you can hope for proving regularity for the original solution. And that's exactly what you're doing. So it's, this is a crash cheap course in partial regularity, whose idea is very simple, and it's given by DeGeorge in 59 or 60. And that's, then everything, all the rest is a variation on this scheme. This is nothing. Okay. That's essentially what I was saying. That's essentially what I was saying. Okay. And now we have the problem that we have a right-hand side, and therefore we go back to the modified potentials I introduced yesterday, and the one we used with the Totti Daskalopoulos and Tuomo Cusi to treat fully nonlinear elliptic equations. So in the case of fully nonlinear elliptic equations, the idea is that the right-hand side is not allowed to be a measure because the whole equation makes no sense. And the only thing you can treat is then when this is a small variation of Ln. Otherwise, Alexandrov-Bakerman-Pucci principle fails together with all the rest of the theory. So therefore, we recall that in this case, in the case mu is a measure, what is the Riesz potential? The Riesz potential is f over b rho over rho n minus 1 d rho over v over rho. So this you can do this. This is an integral, so you can rewrite down in the following way as the average of f over b rho. It's just the rewriting of the Riesz potential. Now the Riesz potential is not allowed here because this has, in some sense, you have to cook up a potential which starts acting on the let's say larger space for which the equation is defined. Here the larger space is of course this guy, so you apply Elder and you do the following object, and this is the modified Riesz potential. This is nothing but a modified Riesz potential that it can be rewritten as a Burke potential. So this is very often used in the literature. Okay, we introduced it in that paper because the idea was that then we found that it has been also used in other contexts, essentially. It's a nonlinear potential which is suited to the problem. So, okay. For general systems, a theory of equations with measured data is not allowed until you get the P-Laplacian system for which we already have everything. And therefore, also in the case of systems, we go to the Riesz potential, to the modified Riesz potential. So the idea is that to match partial regularity and potentials, we will use this modified Riesz potential, which is a Burke potential. It's nothing but a rewriting. It enjoys all the same properties, all the same mapping properties of Riesz potentials. So the only difference is that I1 starts acting from L1, and so it gives you all the mapping estimates from L1 and so forth, and this starts from the minimal Q here. So it starts acting from LQ to all the other spaces, but all the mapping properties are essentially the same. There's no difference because mapping properties of potentials, they just depend on the rate of homogeneity and on the scaling of the kernel. And since here everything is homogeneous because it comes from Elder, then you have made no modification whatsoever. So all the mapping properties are the same. So no difference. Okay, that's the catch. And that's the idea. You have a general system, and now you use the, okay, of course there are two things. You want to recover the potential estimates, and you want to recover the partial regularity theory. So therefore, we say that there exists a universal epsilon such that if the axis plus the potential is small, then you get exactly the same thing that we had yesterday. You have a Lebesgue point for the gradient, because this was the basic conclusion when you have the finite Riesz potential. So you have a Lebesgue point for the gradient, and then you finally get the potential estimate, the local potential estimate at the same scale. Yesterday we have seen that one of the main consequences of the Riesz potential estimate, and it's one of the main consequences because it reproduces in the nonlinear setting the classical criterion. The classical criterion of Choquet-Berlot in the classical potential theory is that if you have a P-Laplacian equation, then if the Riesz potential at a point is finite, then this implies that x0 is the big point for the gradient. And that's exactly the same thing. And then this comes along with the potential estimate. So you immediately see why this is natural, because they both have to be close they both have to be small. Of course, this is essentially the same thing that prescribing that this is small. Why? Because you know that when this guy is finite, then when R is small, then this gets small. So this is just about the solution. This is just a more aesthetic way to express them both, but it's really again only partial regularity. Because you know that if this object is finite, this is an integral, because this is this guy. So when capital R goes to 0, this goes to 0 and becomes small. It's the real thing, it's what it must be. It's about the axis. So this is a way to say that the axis is small. Then you can always shrink with the potential. But I like to express them both in the following way because for aesthetic reasons. Okay, why this condition is natural? Essentially, we refollow the previous argument. When this system is close to this system, this is the good. This is the good system. The second one is the linearized system, and the first one is the original one. In order to be close to the linear system, you need that the operator is close to the operator, but in order to be the operators to be close, then the U must be close to its average, and this means that the axis must be small. But also, the right-hand side must be close to 0. The right scale that encodes the partial regularity is the Riesz potential and the smallness of the Riesz potential. So the smallness of the Riesz potential tells that the right-hand side is close to 0 in the right scale to allow for the existence of a Lebesgue point for the gradient. So you immediately see this tells you that the nonlinear operator is close to its linearization, and this tells that the right-hand side is in the right scale close to 0. And therefore, you can still implement all these facts. Of course, this is an intuitive way of saying things, and it becomes more technical to implement that. That's the summary of what I was saying. Nothing. And this is essentially the sharp catch between partial regularity and nonlinear potential theory. Essentially, this is the first paper I know where the two universes start talking to each other. In particular, we can show that if the potential goes to 0 uniformly, then you get partial regularity. And this is exactly the sharp partial regularity analog of the sharp, continuity criterion that I told you before. If this guy is close to 0 uniformly, then du is C0. Here, if it goes to 0 uniformly, du cannot be C0 because partial regularity is there anywhere, but at least the full partial regularity is where you expect. So in some sense, we decouple the partial regularity from the Riesz potential, and we detect the right Riesz potential to reproduce the partial regularity theory in the sharp way. And once again, we have the same object here. And finally, the final approach, once again, if the right-hand side is in Lorentz, is in the right Lorentz space, then you have partial regularity. Of course, if it's not in the Lorentz space, then the singular set can be full measure, because you can put singularities everywhere. So this tells you that if the right-hand side is in the right Lorentz space, that is the best possible one in view of the standard even linear elliptic theory, then you get the partial regularity of the gradient. But partial regularity must be there. So the final outcome of this paper tells you that if you use potentials, partial regularity can be described via potentials exactly as the full in the vectorial case, exactly as the full regularity can be described via potentials in the scalar case. I mean, there's no. This is the catch between the 2 points. For instance, you can get this. This is the analog of Caffarelli's criterion for fully linear. This provides PMO, for instance, and then you can go on with essentially all the results can be reproduced from the scalar case to the vectorial case with exactly the same condition on the potential, but paying attention to the fact that you have to replace full regularity by partial regularity, of course, because this partial regularity is there nevertheless. I mean, independently of the right-hand side. And that's the end of the lectures. Thank you.
Thank you very much. Are there questions or remarks?
So how's the Hausdorff dimension of this?
Oh, there are also estimates for the Hausdorff dimension. It's not the case to bother the audience with that.
I don't want to be bothered too much.
Yeah, okay.